Hi, and welcome to Engineering 255. This video is going to be about Chapter 6. We're going to start to look at how do we do a structural analysis. When you have a big structure, how do we analyze the forces? How do we know the internal forces so we can design the object to sustain the load? So that is the topic of this chapter. There are two very important methods that we are going to look at in the chapter 6. The first method is called the method of the joint, which we will look at in this video. The next method is called the method of sections. That is going to be in the other video. So let's dive in to see what are we going to learn right here. So the objectives for this video is that we're going to define a simple truss. The truss is a structure based on a simple shape, and normally it's a triangle shape. We can extend this triangle to expand to such like a bridge structure that you can see in the picture. And second thing is that we're going to determine the force in the member of a simple truss. And the method we're going to use here is going to be the method of the joint. We're going to explain what the method of the joint is. And there's a very special thing called a zero force member. And this is going to be beneficial if you have a very complicated structure, and the zero force member simply means that member doesn't have an internal force. And that will help us to simplify our calculation. And how do you know which member or members are zero force member? That we will give you an idea. We always like to start with some kind of application idea. So truss. So truss is very common structure that we use in the supporting big structure, such as a roof. And then you look at the outside of the house, and they all have this kind of truss structure. What we wanted to know is that when you are designing any of this structure, how do you know the material that you select or the size of the beams are stronger enough to support the load? To do that, you have to analyze, and you have to make some assumptions, such as that you want to design a house that can support certain amount of the wind, and the wind is going to give a wind pressure. The wind pressure can be converted into a wind load, and then we can design the proper size of the structure. This could be also like a mechanical system, like a crane. And when you design a crane, you can see all this steel are like a structure of the truss or the bridge, right? So this is where we are going to apply by learning this method. Let's take a look at a very simple truss structure. So again, here we just define a truss is a structure composed of a slender members joined together at their endpoints. This is very important. It's going to be joined at the endpoints. Okay. If a truss along with the imposed load lies in a single plane, then this is called a planar truss. In our study, we're going to start with a planar truss. There is a 3D truss as well. The calculation will be like similar to what we did before. You're going to extend it from 2-dimension to 3-dimension. So you're going to have an X and Y, then you're going to expand to X, Y, and Z. We're going to start with a 2-dimensional, so you understand the idea, then it's easier to expand it to the 3-dimensional. And as we said, a simplest truss is just a triangular element. So you look at the picture, we have A and B and C. This is a simple truss structure. You can expand this either going from B to D and going back to A, or you can extend to the right with another triangle goes to the right as well. So that would be like a B and C, maybe there's a D, which is a mirror to the point of A. Um, for this kind of a trust, the number of the members and the number of the joint are related by this equation. So N represent number of the member, J represent number of the joint. So how do you see that from this picture? Let's see, look at this picture here. So how many joint do we have? Joint represent that you have two members at least that they join together at the same point. So we have 1 and 2 and 3. 3 joints in this picture right here without the dashed line here. So 3 joined, you use 2 multiplied by 3, that will be 6. 6 minus 3, that means there's 3 members, which is AC member, CB member, and AB member, right? That is what this equation represents. Let's try a little bit more complicated. Let's just extend including the dashed line here. So instead of a 3, now we have 4 joints, right? A, B, C, and D. How many members do we have? 1, 2, 3, 4, 5. We have 5 members. Let's see if this equation gives us 5. So instead of 3, we now have 4 joints. So 2 times 4 is going to be 8. 8 minus 3 is going to be 5. And that's why we have 5 members here. Okay. So with the idea of the basic trust, now let's look at how and what are we going to do with the trust. Well, the purpose of our chapter is to study how to analyze the force. So the purpose of that is that if you want to design a truss, you wanted to know how much force that is applied to the member so you can select the proper size of the member to fulfill your structure. And to do that, we make 2 assumptions. The first assumption is that we're going to say all the load are applied at the joint. And we also going to say the weight of the truss member itself will be neglected. So we're going to ignore any of the weight of the members. This is reasonable if your load is mainly due to the load from the external. So you consider about the external load, right? So if you design a structure and it's without any of the external load, you have to make sure the structure itself can be self-sustained. So it should be, otherwise you're not analyzing anything. But we are more considered about the external load, and we wanted to see what this external load can cause the force inside of the material. The second assumption is that we're going to assume all these members are joined by a smooth pin. Okay, so what is a pin? We talked about this in the previous chapter. Pin is a supporting element that allow you to rotate, so you can have moment to rotate. You don't actually have moment because it's free to rotate. The supporting pin will support the f of x and the f of y, so it only support the force. So that's a very important assumption. So based on those 2 assumptions, your member of any of the member in the truss can either be under the tension or is under compression. Okay, we are not going to consider a situation called buckling. Buckling meaning that it will bend, it will change the shape, meaning the member itself buckle, it curved. But in this case, we're not going to consider that situation. The member will be still the same shape, but it's either to be compressed or it's be pulling in under tension. Okay, now we are going to go into the detail how to do the calculation. But first, before we go into the calculation, let's look at some of the basic stuff in here first. So here we have very simple example. We have a triangle shape right here. So we have a point A, we have point C, we have point B here. and there's an external force 500 Newton on the top at the point of B. The configuration is given by the dimension. You have 2 meters in here, 2 meters here, so it's a 45 degree right here. You can calculate the length of this one is going to be square root of 2 meters. That should be 2 times the square root of 2. Okay, so when you wanted to solve the force by using the joint method, you're looking at the point, which is a pin for each one of this point. And you can select any of the pin to start with. So let's say if we are looking at a pin of the B here, this is the pin of the B, and we just wanted to draw a free body diagram of this point at here. When you do a free body diagram, we're going to cut the member. We're going to cut a member right here. When you cut the member, you are going to put some supporting force, right? So in the point of B, you have an external force 500 Newton, which is right here. When you cut this BC beam, you're going to have a force of the FBC, and you put FBC here. And you have another force, which is FAB, and this is FAB here. Now, how do you know this is a compression, or how do you know this is a tension? Well, normally you probably don't know, but you can kind of guess. How do you guess? Well, if you have an external load here, 500 Newton, and it's pulling to the right, and this one just go vertical downwards, so this has nothing to do with the 500. If 500 pulling to the right, I need to balance the force to the right. This one has to push to the left. So FBC has to push to the left. It will go into this point of B. So this is kind of what we call the compression force, meaning you are compressed the point of the joint of B. And if this one compresses, so you have certain amount going upwards, right? FBC has certain amount going up, certain amount go to the left. So to counter the force going up, I have to make this one going down. So this one has to be pulling the B away, which is what we call the tension. So, but it's okay if you make the wrong assumption, because when you do the calculation, if you calculate the BC, which is negative value, and you made an assumption that's going outwards, it simply just tells you that your direction is wrong. Your actual direction should be opposite to what your assumption is. So it's okay. You can make any direction assumption. However, your answer will justify your direction. Okay, so let's just give you a general idea about the step of the analysis. So the first, when you have a truss, you need to draw a free body diagram, okay, of the entire truss, because we want to find the supporting reactions. Okay, so the first step is to find the supporting reaction by the entire free body diagram. This is needed so we will get enough information to use the method of the joint to solve the problem. And the second step is that you're going to draw the free body diagram of a joint. So this one is free body diagram of the entire, and you solve the supporting reaction. And second step is you pick a joint and with one or two unknown, and you draw the free body diagram of that joint, just like the one that we show you in the point of B. And you can assume that all a non-member of the force is in tension. Okay, unless you know that is going to be in compression. And again, this is really not necessary, but making this assumption might be easier for you to select. And the third step is that you just simply use the equilibrium equation, which is summation f of x equal to 0, summation f of y equal to 0. And if the answer is positive, is tension. If answer is negative, is compression. That's what I just told you. And then you're going to repeat the same process to another joint until you find out the answer that you needed. Let's talk about the zero force member. Zero force member. So here you have a structure, which is a truss. How many joints do we have? You have A, B, C, D, E, F. 6 joints, right? And we tell you the member is equal to 3 times joint minus 3. So we have 3 joints, and you can have what? 6 times 3 is 18 minus 3, that's 12. Do we have 12 members? 1, 2, 3, 4, 5, 6, 7, 8, 9. No, we don't have that much of the member. Well, the member actually is the maximum number of the members. So you don't have to have that much of the member. But with this 6 joint, if you use the method of the joint, meaning you have to solve 6 joints, and each one of the joint you're going to have the summation f of x, summation f of y. You're going to solve the problem. It's going to take forever. So this is some way that we can simplify this calculation, which is that if you can identify some of the member that doesn't going to have any of the force, then the force itself is going to be 0, then you can save a lot of time. And how do we define the zero force member? So let's look at what this definition is. If a joint has only 2 non-collinear members and there's no external load or support reaction at the joint, then those 2 members are zero force members. Okay, so what is collinear? Collinear meaning these 2 members are like on the same line. Like this member right here, and you connect with another member at here. This will be like a collinear member. So we're not consider of this situation. We consider of 2 members, they connect with certain angle. And in this case, A is one of the situation. What A is one of the example. And it's not only about how these 2 members are connected, it also has another condition, no external load. So if you look at A, there's no external load, right? Like this one has an external load. And the other situation is or support reaction. What is support reaction? This is what we call a support. This is what we call the support. So if you look at this one here, then this one has external support. So we cannot use this one as the zero force member. For this, you have 2 members. They are connected, not collinear. There's no external load on point A. There's no supporting load reaction at point of A as well. So this satisfies with the situation, the zero force member. That means this AF and AB are zero force member. AF, AB are zero force member. You can just ignore this. This is not going to give you any of the force. This is not going to give you any of the force, meaning this member doesn't support anything. Same thing if you look at this right here. This is theta is not like 180 degree, meaning they are not collinear, and there's no external load. There's no supporting load here. So this one is a zero force member. This is zero force member. Okay, let's look at this one here. When you have this one zero force member, this zero force member, you can simplify your problem to this one. Now the number of the joint become 1, 2, 3, and 4. You simplify the problem to analyze 4 instead of 6 joints. If you have 3 members from a truss joint for which 2 of the members are collinear, and there's no external load of the reaction at the joint, then the third non-collinear member is a zero force member. So this is the case if you have 3 members, okay, 3 members. The previous case is we only have 2 members connect at the point where the point doesn't have external load, there's no supporting load, then these 2 members are zero force member. Now here is the 3 members connected, and there's one of them is not collinear. So we say collinear meaning they are on the same line, like this one here is collinear with this one here, and at the point of D you have the third one, which is going to be AD. And when you have that case, these 2 still carry load, but this one will be zero force member. So zero force member have 2 situations. And what about this one here? This one is collinear with this one, and this one is not collinear with this one. And when it's not collinear with this one will be zero force member as well. So we can simplify this one to this case. So you only have a big long member and here, and these 2 are zero force member, and then you simplify this one to be 3 joint. Let's use a complete example to explain how you use this idea to solve the method with the method of the joint. The picture shows a simple truss, and you have 2 triangles, and the number of the joint is A, B, C, and D. First, let's look at, do we have a zero force member? Okay, we have 2 cases. If you have 2 members, no external load or no support reaction. Okay, this one there's a reaction, right? A reaction is from bottom. This is the rotor, so the reaction is going to be this. Here, this is the ping, so we have 2 reactions. One is go this way, one is go this way. So there's 2 reactions. This is the ping, so there's 2 reactions. This one you have an external load, so this one certainly is not going to be. So for each one of those, what about this one here? Well, this one is not 2 members. This is 3 members. Okay, so what about 3 members? If you have 3 members, 2 of them are collinear and the other one is the 0 force member. So this is the case where your B and D is going to be 0 force member. So we can actually simplify this one just a big triangle. This will be just a very big triangle. Okay. Now the first step for this kind of a problem that we said before is that first you find where the reaction force is by using a big free body diagram. So let's look at the next step. So we look at the big pictures to find the reaction force of the supporting point. So I'm not going to look at this one first. I wanted to look at the overall picture first. So this is the overall picture. This is the entire free body diagram. We have an external load here, which is a 450. We have a reaction force. This is a roller, so there's a AY, and we have we have a reaction force at this pin here, which has 2 components. One is this way, and one is this way. Now you can certainly make assumption to the right. Let me just make positive direction. This will be CX. This will be CY. So how do we determine the AY, CY, CX? We have 3 unknowns. How many equations do we have? Naturally, you probably only think about, summation f of x, summation f of y. Yes, we can use these 2 equations. So if we use summation f of x, then Cx is the only force in the x direction. No, there's a 450 equal to 450. What about AY plus CY equal to 0? So now I solve the Cx. How do I solve AY and CY? Well, to solve these 2, you need one more equation, and the third equation is summation moment equal to 0. So where is the summation moment that you will use? You can pick any of the point. You can pick point of A, you can pick point of C, you can certainly point of D. So here's the D, here's the A, here's the C. If we select the point of C and you make this one equal to 0, then Cx and Cy will not make contribution of any of the moment because these forces apply to the same point of the reference point. There's no lever on. If you look at the AY, the AY will create a moment around this point of C, go this direction, right? And this moment is going to be equal to AY times the distance. The distance will be the distance of AC, which is going to be 4 feet, that'll be 8 feet. This one make it go clockwise. Where you look at the other force, which is this force, this external force 450, will make the object rotate in the counterclockwise around the point of C. So this one will create a moment which is a 450 times the lever arm, where the lever arm should be this distance, 4 feet. So 4 feet. And these two, you sum them together, should be equal to 0. This one of them is negative, which is this one here. This is a positive. So when you do the calculation, and you will find out the a sub y is 225. Because let me just write it here, 8ay minus aay plus 450 times 4 equal to 0, and you can cancel this to 2 and divide 2, you got 250, right? So AY is going to be 250 pounds. If you have AY equal to 250, your CY is going to be negative 250 pounds. So that means your reaction at here is going to have a force right here, which is 250. Right, this one is the AY, yeah, then 250. And you have Cx, which is 450. And your Cy is going down, and that's 250. Okay, then we normally can start from this point to analyze the force on this member and this member, but you can also choose the point of D. So in this case, they choose the pin at the D. If you choose pin at the D, you're going to draw the free body diagram around the D. You're going to cut this one, cut this one, cut this one. But this one is a zero force member, so you can ignore this one. You only have this F of AD and F of CD, and you also have external force. Notice that, how do you know this force direction? This force always go along the direction of the member. So it will go along this line here, it will go along this line here, and the book recommend that you assume the force is going to be in tension. In this case, you can make an assumption as compression. It really doesn't matter. So if you do the free body diagram on this part here, you got this one here. And again, you can just use summation f of x. In this case, you use summation f of x and summation f of y, which is these two equations, to solve the problem. When you look at x direction, D is x direction, but it's a minus 450. This one will have an x component, which is going to the positive. That will be FCD times cosine 45 degrees. For this one here, it goes to the left, so it's going to be minus cosine 45 degrees. You make it equal to 0. Same thing, you do the summation f of y. You only have these two that give you the y component. So, and you solve these two equations. Then you can solve FCD and FAB equal to these two forces. One of them is compression, one of them is tension. Positive is going to be in tension because we're assuming this force is going outwards. So positive meaning the direction is correct. FAD come out to be negative number, so your actual load at this D here is actually going to be like this. So you have a compression at here, you have a tension at here, and this one is 0. This one doesn't support any of the load. I solved the AXAY already, right? So you can use those information to solve the problem, or you can just draw the free body diagram at the pin of A. We solved this one. We said this one is 250. And we just solved this one here in the previous case, which is 318. Oh, this should be this way, yeah. So this way, right? So that means this one will be in this direction. And this force has to be go along this being here. So here, this is the force of AB. With these three forces at here, you can solve FAB because this is the only unknown that you don't know about. And you can find the solution by using the summation of Fx to find what this force is. So this one has nothing to do with x direction, so you just use 318 and to decompose it, and you can find a solution. I think this one is going up. Okay, so FAD is negative 318, so that means this force actually is going to this direction instead of this direction because it's a negative 318. So you have actually this one go this way, you have this force assume goes to the right, and this one is going up that we just solved before. So then you can find out 318 times cosine 45 degree is going to equal to this FFAB. Okay, and that is going to be 225. Okay, so I want to summarize this. This is a very important topic. We're going to do some more example in the lecture. So first you have to know what is a simple truss. Simple truss normally just a triangle shape. You can expand it by extending the triangle to the other direction. Zero force member, we have two cases. If you have two members, you have three members. If this two member no external force, no support, then these two members and non-collinear, then these both members will be zero force member. Three members, two members are in collinear, and the third one is the zero force member. The method of a joint, you have several steps. First, normally we will do the overall. You first find the supporting forces, and then you choose a joint. and to solve. To solve the member force until you solve the complete solution. So we're going to see you in the next video, and the next video we're going to talk about the other method, which is the method of the joint.